Welcome, Math Explorers. I'm thrilled to welcome you back as we once again immerse ourselves in the captivating world of mathematics. So, today's focus is on a concept that shines brightly in the realm of topology, notably the Baire Category Theorem. Now, you might wonder, why are we zeroing in on this particular theorem? But the answer is truly captivating. The Baire category theorem is not just a mere mathematical nugget. It is like a master key that unlocks a treasury of insights. And here is even where it gets more exciting. This theorem is intimately linked to a principle that is a veritable mathematical powerhouse, notably the uniform boundedness principle. But before we dive headlong into this concept, let's first grasp the essence of the Baire category theorem itself. Um, and as a little teaser, we talk about the uniform boundedness principle in the next video. So we start right away, right, with the theorem itself, right? So theorem 2.1. So this is the Baire category theorem itself, right? So let X be a complete metric space, right? So maybe I write let X D be a complete metric space, and let ON, right, be a sequence of open dense subset in X. So let me highlight that the ON are actually open and dense, right? So this means that for every n in n, the closure of ON is equal to X. Then the intersection of the ON, right, is dense in X. Well, just for your recall, just for your attention, completeness here is actually very crucial. So let me highlight it. It's very crucial. Right. So the Baire category theorem can actually be stated also for closed set, right? It is actually very easy to see. Let me write it in another color. So to get the statement for closed subset, right? Observe that ON dense in X implies that the complement of the closure is empty, right? So this means the complement of the closure is nothing else than the interior of the complement. So the interior of this is empty. So to have the statement for closed subset, you see that if I have a sequence, say of closed subset such that the interior is actually empty for every n, then the union, let me write it down here, then the union ON complement, ON is open, so ON complement is closed, so the union is, the interior of the union is actually empty, so something like that. Okay, good. So for closed subset, we require that the interior of the set should be empty, and then the conclusion is that the interior of the union is actually empty. So again, remark, I pointed that out already. Completeness is crucial. Then we will see why. Indeed, put it in another color, right? Indeed, consider the set of rational number. Consider Q equals to Qn such that the n, we will put this right just for you to. So let's consider the set of rational number and consider the sequence. For every n in n, right? Consider the sequence On, which is nothing else than Q minus Qn, right? Then On, right? For every n, say for every n. On is obviously open, right? That's complement of a closed set. It's open. Put it in bracket. It's complement. Of a closed set. Yeah. And it is obviously dense in Q. Right? If you give me any element in Q, and I can always find the sequence of points in On that approximate the point in Q. So, but observe that the intersection of On, right, is actually empty. Well, so Q is not complete. That is what you have to observe, is that the set of rational number is not complete. We put it in color. So Q is not complete. That is why the Baire category theorem fails. Okay. Now let's prove the theorem itself. Proof. Okay. Let On, right, be a sequence of open and dense subset in X. So our aim is to prove that say, put it Z, right, to be the intersection of the On is dense in X. So proving denseness is equivalent to showing that. So we have to show to be more explicit, we have to show that for every x0, say in x, right, any ball around x0 intersect G. So the ball centered at x0 and radius r0. This is different from the empty set. So, well, to start the proof, let x0 in x and let r0 be positive, right? Since O1, right, is dense in x, right? We know that, I mean, the ball centered at x0 and radius r0 intersect O1. So this means there is an element x1 in O1, right? And here I will go a bit one step further, and there exists also a radius, say r1, right, positive, so less than r0/2, such that the closure of the ball centered at x1 and radius r1 is contained into O1 intersected with. Well, I mean, you might be wondering why such, I mean, where does R1 come from, but let me write it somewhere. So such an R1 exists, right? Since O1 intersected with this ball is open, right? So this is, I mean, open as, I mean, finite intersection of open sets, so it's open. So similarly, we do kind of the same trick. Similarly, now with O2, right? O2 is dense in X, implies now we use, I mean, the point we constructed x1 implies that there exists, well, first of all, this implies that the ball this is non-empty, right? So this means there exists x2 in O2, right? And again, there exists a radius for the same reason as above, R2 frequently less than R1/2, right? Such that the closure of the ball centered at x2 and radius r2 is contained into this ball. Maybe just to be consistent, was O2 intersected with the ball centered at x1 and radius r1. But this, observe that this is again contained into the ball centered at x0, radius r0, intersected with O1, intersected with O2. Let me just kind of, let me not squeeze it and shift this rather quite a bit. Good. So this is intersected with O1, intersected with O2. So by I mean, if you proceed iteratively, you can basically construct a sequence of xn and a sequence of radius rn. Let me write it. So by proceeding iteratively, one constructs two sequences xn, right, and rn such that the closure of this wall is contained into intersected with the intersection of the OI, I moving from 1 to n, with Rn being between, let me write it properly, Rn minus 1 over 2. Good. So from our construction, it follows that the sequence xn is a Cauchy sequence. We will see why. So it follows that xn is a Cauchy sequence, capital C, of course. It's a Cauchy sequence. Then this is, I mean, kind of a short curve. Indeed, I mean, for every nm in n, right, such that n is strictly less than n, we have that xn belong to the ball centered at xm and radius rm, which is obviously contained into the ball centered at xm and radius r0 over 2 to the power m, right? Because remember, rm was actually between 0 and rm minus 1 over 2, and iteratively, I mean, you see that, I mean the ball of centered at xm and radius rm is actually contained into the ball centered at xm and radius r0 over 2 to the m. So this means that the distance of xn to xm, right, is actually, well, let me go slowly. It's actually strictly less than r0 over 2 to the m, right? So this means this xn, the distance of xn to xm, right, this goes to 0 as m goes to plus infinity. So we indeed have a Cauchy sequence. Now, since x is complete, right, completeness is very crucial, remember. Since x is complete, there exists, say, L in x, such that xn converges to L, right? Because, I mean, every Cauchy sequence in a complete metric space actually has a limit. So, however, as we write it, however, as Sn plus p, right, is actually, I mean, in the ball of radius centered at xn and radius rn for every n positive and for every p greater or equal than 0, right? So you obtain that as p goes to plus infinity, the distance of xn to L is less or equal than Rn. Well, that was quite fast. So, because from this you have that the distance from xn plus p to xn, right, it's actually less than Rn. So if you take the limit as p goes to plus infinity, then you have the distance from xn to L is actually less or equal than Rn. So this means L is actually this holds for every n, of course, right? So this means L is actually into the ball the closure of this ball, right? For every n greater or equal than 0. So this means L belongs to the intersection of all those balls, right? Because the above relation holds for every n. But remember, this quantity is actually contained into the ball centered at x0 and radius r0 intersected with the intersection of ON and greater or equal than 0. But this was actually D, right? This was basically what we set to be D. So this means L belongs to the ball centered at x0. And then we are done. So we basically prove that for every r0 strictly greater than 0, this ball, the ball around x0 intersect G. Nice. Closure of the intersection of the ON, right? It was actually one started before 1, but it's not an issue anyway. So this is equal to x. Good. So we are done. Okay. Now to move further, let's recall some old vocabulary, right? Let's take some definition. Those are, say, old vocabulary. Good. So the first definition is set is subset. Say set, say M, right? Subset M of X in a metric space. X is called nowhere dense if the interior of the closure of M is empty. Let me use this color. Well, the interior of the closure of M. This is the interior of the closure. It's empty. And then the second definition, M is called of first category. If M is a countable union of no word set. So a set is a first category if it is a countable union of no word set. So if M is a countable union of nowhere then set. Then you have the last definition. So M is called of second category. It's called of second category. I mean, if it is not a first category, so very easy. If it is not of first category. Good. So let's state our first corollary. Corollary. Zero one. So in a complete metric space X, right, the complement of a set of first category like this in X. In a complete metric space, completeness is crucial. In a complete metric space X, let me put it in color, the complement of a set of first category like this in X. Of a set of first category, right? Like this in X. Okay, let's have a look at the proof. Okay, just recall all the settings. So let X be a complete metric space. We give ourselves a subset M of X, right, which is of first category. Right, remember the set is of first category if it is countable union of nowhere then set. So that means M is actually union over of Mn, right, with Mn nowhere dense. The interior of the closure is empty. So we want to show that the complement of M lies dense in X. So we want to show that the closure of M complement is equal to X. Okay. Well, you have M complement is nothing less than the intersection of Mn complement. The complement of the union is the intersection of the complement of the set. So, however, we know that a set is always contained in its closure, right, for every n. So this means that the complement of the closure, right, is contained into Mn complement for every n, right, which means that the intersection of this, right, over n in n is contained into M complement, right? No, let me write first into this intersection. But this is nothing else than an M complement. So let's call this relation star want to make sort of ellipse. Sorry, but took forever, but we are done. Okay, let's call this this relation star. I will refer to it later. In fact, why will this relation be useful, right? In fact, because I know that this is actually contained into M complement, and then I want to show that this is dense in X, so it is enough for me to show that this is dense in X. Because if I show that this is dense in X, I'm done. This will, automatically the complement of M is actually dense in X, right? Because this dense means that the closure of this, right, will be X, right? So you have X is contained to M complement, which basically conclude the proof. Okay, so since the Mn are actually nowhere dense, right? Since the interior of the closure of Mn are empty, right? For every n in n, right? It follows that the complement is actually equal to X, right? For every n, of course. But the complement of the interior is nothing less than the closure of the complement. So I say it once again. The complement of the interior is the closure of the complement. So this means this, right, is equal to X for every n, right? So this follows from this, of course. Follows from this, right? Because I said the complement of the interior is the closure of the complement. So this holds for every n, right? Since this Mn closure is always closed, as we know, right? So since this complement, so the complement will be open. So since this is a family or a sequence of open and dense subset of X, it follows that It follows from the Baire Category Theorem. Follows from the Baire Category Theorem that the intersection is dense. When it's dense in X, right? So star, right? Remember we had the inclusion. So star then implies that complement is dense in X. So this concludes the proof. Okay, let's have a second corollary. So this first corollary actually enables us to state this second corollary. I mean, in the complete metric space, a complete metric space itself is always and always of second category, always and always. So corollary 0.2. Complete metric space. Complete metric space itself is of second category. I mean, this is rather easy to prove. So let's have a look at the proof. So you can never write, I mean, the complete metric space as a countable union of lower dense set. That is just impossible. I mean, as far as I know. Okay, so let X, right, be a complete metric space. So aiming to a contradiction, right? We assume that aiming to a contradiction. Assume X is of first category, right? Then by corollary 0, 1, we highlight it very quickly. Then by corollary 0, 1, right? X complement, right? The complement of X lies dense in X, right? So basically what you are saying is that the empty set is dense in X, right? Which is absurd. I mean, which is absurd, right? As so let me put in here, this is absurd. So this ends this proof, and then I think we will take probably the last corollary for today, maybe the another corollary that is also, I think, very important for you to know. Corollary 03. So In a Banach space, every basis in the sense of linear algebra, right? Every basis in the sense. I'm recalling the sense of linear algebra because, I mean, in Hilbert spaces, we also have, notion of basis that is quite different from the notion of a basis in the sense of linear algebra. So this is actually noteworthy to highlight that. So in the Banach space, every basis in the sense of linear algebra, put it in color, has either finitely many or uncountably many elements. Again, just recall Banach space. Okay, proof of this claim, of this corollary. Again, we will actually argue by contradiction. Change the color. So let X be a Banach space. And denote by B, right? Denote by B, right? Capital B, a basis, right? A basis of X, the linear algebra sense. So assume B does not have uncountably. So I mean, if you want to show such an assertion, right, that B has either finitely many or uncountably many elements, you either assume that one is false and then you show that the other one is necessarily true, right? That is basically, how to prove it, how to go about such proof. So assume that B does not have uncountably many elements. So we assume that the other assertion is false, uncountably many elements, right? And put it in color. Let's prove that B is necessarily finite. Oops, good. So, aiming to a contradiction, right? Probably not really a contradiction, but well, quite a contradiction. Actually thinking of how to put it. Well, not really a contradiction. So assume assume aiming to well, let me say aiming to a contradiction. Let me put it that way. So aiming to a contradiction, right? Assume B is countably infinite. It's countably infinite, right? So that means B can be written as, it's bk, k in n. So, and let's consider now, the proof is a bit constructive, right, but it's not difficult. So let's consider, say, un, right? Define un to be the span of b1, b2, up to bn, right? The span. This is just my notation of the span, right? Some of you might be familiar with that, some of you might not, but just know that whenever you see this, this expression, just know that it refers to the span of the vector b1, b2 up to bn. So then, for every n, right, un is a closed linear subspace. Closed linear subspace, right? Closed linear subspace of x, y, let's put it in bracket. Every linear subspace of finite dimensional is closed, right? That you can prove it. Every linear subspace of finite dimension is closed. Okay. So, so un is closed, and then we have x, which is the union of the un, right? This is just basis property. Let me put it another column, right? This follow from basis property, right? Because B is actually a basis of X, so every element of X can be written as linear combination of element of B, right? So X is obviously equal to the union of the UN. It's very easy to prove. I think it is rather clear, right? We don't need to prove that. Okay, however, as X is a complete metric space, right? It's a complete space, right? It is of second category. That is what we know. It is of second category. That means there is at least there is an n in n, right? Such that u capital N, right, is not lower dense. It's not lower dense. So that means that the interior of the closure of un is different from the empty set, right? But un is actually a closed linear subspace, so this means that the interior of this is non-empty, right? So this means there is this Cx in un, right? And there is an epsilon positive, such that there is this x in the interior. X being now in the interior of un means that there is an epsilon ball around x that is contained to un. So the ball centered at x and radius epsilon is contained to un, right? Now, because because UN is a linear subspace. Because UN is a linear subspace, right? It is stable under translation. And commutative. So this means that the ball centered at 0 and radius epsilon is, just to go step by step, the ball centered at 0 and radius epsilon is contained to UN, right? This also means that the ball centered at 0 of an arbitrary radius r is contained into UN, right? This is for every r positive. Right? Each of those steps are not actually difficult to prove, right? So this means x, right, which is equal to the union of the ball is contained into UN, right? Well, for those familiar with topology, so this equality, just follow from the fact that X is the topological vector space. So, but if you're not familiar with that, that's fine, right? We can always prove that X is actually the union. If you give me any element in X, I can always find a ball around that element that is contained into the ball centered at 0 and radius r. And remember, X is closed and open, so everything is smooth. So X is actually a topological vector space, right? Maybe just for your understanding, for those who for those familiar with topology, this is just for you. Indeed, the union of open balls, right, forms the topological basis of X. So, since you have X containing that is contained into UN, right? This means that the dimension of X is finite, right? Because UN is finite dimensional. So if X is finite dimensional, then the basis of X should be, it's necessarily finite. So this means B is necessarily finite, and this ends the proof. Okay, so this leads me to actually draw your attention on the particular fact, right? But I think this corollary is also it's actually it's also important, right? Just for your knowledge, right? It might not have anything to do, but just for your knowledge, and also as an application of what we have been, we stated above so far. So the vector space of polynomials, right, with an arbitrary norm is never and never complete. And then we will prove that. So the vector space of polynomials, right, with an arbitrary norm put it in color. It's never, capital letter, right, for you to remember that. It's never complete, never and never. So if you enter the space of polynomials with any norm, it is never complete. This is just a consequence of corollary 03, right, that we just proved, right, that in a Banach space, I mean, every basis is, in the sense of linear algebra, is either finite or uncountably infinite. Okay, proof. So let P, call it capital P, let P be the vector space of polynomials. Of polynomials endowed with a norm. Say this norm. So we assume that, I mean, it is complete, right, by contradiction. So assume P is complete. Then according to the previous corollary, right? Then according to corollary 03, let me highlight that. Any basis of P has either finitely many or uncountably many elements. But put it in color, right? The monomials form countably infinite basis, right? Which is a contradiction. Good, and then we are done. Okay, I think we are going to stop for today. So thank you once again for joining me, and see you in the next video.